We know the world around us by means of the 6 senses. Vestibular apparatus, skin, tongue, nose, ears. But mostly, we rely on eyes. Vision accounts for almost 90% of all the information we get. Our vision system is incredibly complex and terrifically perfect. And it is exactly what helps us to see electromagnetic radiation with wavelengths from 380 to 780 nanometers, which we call light. But our eyes deceive us. In fact, what we see is only a small part of the world with all its variety of electromagnetic waves that surround us remaining invisible to us. How to see the world in pink? Why compress the color, and what does the swing have to do with it? And what does the temperature look like? And where can you hide from radio waves? And are these invisibles safe? In the 20s of the 20th century, Russian physiologist Vasily Danilevsky wondered whether invisible electromagnetic waves affect a living organism. He conducted a series of experiments with the preparation of a frog's leg and the electromagnetic field, and he realized direct impact of the current is not necessary. It is enough to place the exposed nerve in an alternating electromagnetic field, and bang, the leg comes to life. Terrific. The leg continues to contract even a few minutes after. Amazing. This seemingly very simple experiment was the one which, for the first time, clearly demonstrated and proved electromagnetic waves, invisibles. We do not even notice their presence, but they have a direct impact on the nervous system of living beings, and therefore on us. But we will get back to that later. And now, what is it all about, these electromagnetic waves? No, the sound of the piano is also a wave, but a mechanical one. It depends on the environment where it spreads, like now, for example, in the air. But with the help of this musical instrument, it is very easy to explain the others, electromagnetic waves. Bravo, Rustam. Can I still sit up for a while? So, if you imagine that one octave, which is 7 notes, it's 7 primary colors. You get Richard of York gave battle in vain. This is the visible spectrum of electromagnetic radiation. Our light, all the light we can see, is only 1/10,000,000,000th of all the electromagnetic spectrum. And to imagine the whole spectrum, you need to continue this keyboard for another 7 trillion notes. That's a nightmare. Taking into account the width of the keys, this keyboard would be longer than 100 million miles, even more than from the Earth to the Sun. What a grand piano. And all of this usually remains beyond our vision, usually, but not today. And for starters, let's speak about the nature of electromagnetic radiation, which is the same for all this spectrum. The universe consists of atoms, which in their turn consist from a positively charged nucleus and electrons. All the elementary charged particles interact with each other by means of the electric field formed around them. When the particles move in a focused manner, the electric current appears. But as soon as the charge begins to move with acceleration, the electric field around it starts changing. It creates a vortex magnetic field. Together, they form an electromagnetic field that propagates from the charge in the form of an energy-transferring transverse wave. In a vacuum, its velocity reaches the speed of light. In a medium, it depends on this medium. And the form of the electromagnetic wave depends on the length and the inversely proportional to its frequency. And we will probably start with the spectrum we are familiar with, visible light. Alexander Lvovsky is one of the most famous quantum physicists in the world, and he knows how fascinating ordinary light can be. Alexander, so what is light?
Well, there are two concepts of light. The first one is that light is a stream of particles that are now called photons. And the second is that light is a wave. Well, quantum mechanics, it seems to have united these two concepts into one.
Well, so what is darkness?
Darkness is when the light is off, no photons.
So this is the usual for darkness?
Yes, what our eye perceives. Our eye is a photon detector.
But you realize that even when there are no constituent photons in the light still exists, right?
It wasn't me who realized that. Quantum physics realized that. That is, the quantum theory of light was able to combine these two here, these two theories, and to show that light is both a particle and a wave. We can say that it is a stream of particles with wave properties.
If it wasn't for this new understanding at the beginning of the 20th century, lasers would not have appeared, for example. By the way, they are the main instrument in this optical laboratory.
Yes, this is a laser, an impulse laser, that produces red light. Here we need to convert it first. We need to make it blue. It happens here in this crystal. The frequency doubles. The frequency of light is doubled. The wavelength is reduced by half. Red light forms blue.
Wow. And then the secondary ray begins a journey through the whole labyrinth of dozens of mirrors and lenses mounted on a special table.
Optical table is this massive metal tile. You see, on the one hand, it's very heavy. That is, it weighs approximately like a car. On the other hand, if I touch it, you will see it move.
So, it literally hangs in the air?
Yes.
This trick allows you to extinguish any small fluctuations. All of this in order not to bring down the exact adjustment of this labyrinth.
Some of these mirrors, if we move them literally a micron, the installation will stop working.
There are no windows in the laboratory, and the walls are painted black, not coincidentally. If another light photon hits in here, it will be absorbed by the walls and will not affect the experiment, because its first stage is the creation, attention, of a light vacuum.
But we can block the laser device here. Here it stopped, and it doesn't go further. Then the simplest quantum state of light, a vacuum state, in which there are no photons.
That is, there are no photons, but something is after all.
Even when there are no photons, the electromagnetic wave, all the same, has the non-zero amplitude, non-zero value. And on this oscillograph, you see that even when there are no photons, there is a certain noise, and this noise is quantum fluctuation of an electromagnetic wave. Absolute darkness does not exist. There is always some kind of radiation that the human eye does not see, but other devices, such as a thermal imager, see it.
The thermal imager is able to capture the infrared spectrum. On the piano, it is on the right from what we are able to see. Electromagnetic waves are longer here. We feel their energy no longer as light, but as heat, but usually we can't see it. But we usually have a real experiment to test what your thermal imager is capable of, and now I don't know whether it's capable to cope with the task. We invited a cat and Vladik. Vladik, hello.
Hello.
What is the name of the cat?
Masya.
Barely noticeable even in the spotlight, this cat is pitch black. Just what we need. Try to find a black cat in a dark room.
When I walk around the apartment at night, I stumble across it a lot.
But apparently we have a salvation for you, because Dmitri says that the thermal imager will find a black cat in a dark room easily. Do you believe it?
Yes.
Let's try it.
Yes.
We should check, right? Well then, let Masya go. Oh, it doesn't want to go anywhere. Well, let's turn off the light. In the pitch darkness, Masha seemed to disappear. Her black skin absorbs all the visible light, reflecting nothing. So where's our cat?
We'll find out now.
But electromagnetic waves are a dead giveaway for the fugitive. Oh, here it is. A bright golden spot and not a black cat. But you should agree that if you had a thermal imager, most likely you would stop stumbling across it.
Well, yes, at least by chance.
The cat's temperature is almost 2.5 degrees more than the human's, but fur is a good heat insulator. Therefore, Masha radiates not very intensely unless it's flushed muzzle. And over there, exactly where she has a little baldness,
Yes, there is less fur there. The radiation passes more intensively.
well, that is why we have pets in the first place, for the feeling of coziness and warmth. And the thermal imager easily finds this warmth. And what if we take something colder?
Let's try.
Let's check.
Yes.
We'll check. Of course, I could not ignore my favorite substance, but the thermal imager does not give up. In the infrared spectrum, it looks like a bowl of nitrogen, absolutely purple, and blue, and green. That is it so cold that our thermal imager begins to rush about,
Yes.
to go a little bit crazy? And yet it continues to detect. Here, for example, grapes. We're putting it in. Nitrogen begins to boil immediately. And we see the berries turn from orange to violet. And our grapes are absolute ice. Just absolute. But if the infrared spectrum is heat, then how can the thermal images detect negative temperatures?
Even close to absolute zero, there is still some kind of thermal radiation.
Is there such a temperature? Absolute zero? And how many degrees is it?
Well, it is basically unattainable.
Minus 459.67 degrees Fahrenheit. At this temperature, the energy of thermal motion of atoms and molecules of a substance must be zero. We say must be because this absolute zero is absolutely unattainable within the framework of thermodynamics of our universe. So in the native macrocosm, all bodies emit electromagnetic waves. Well, are you worried, no?
A little bit.
So am I a little bit. My favorite and most spectacular trick with liquid nitrogen, just add boiling water. 1, 2, 3, go. Ooh. This is also stunningly beautiful in slow motion. The difference of temperatures causes nitrogen to boil out at a flash, forming a cool and flowing cloud. And in the infrared range, it turns out to be a completely multicolored fountain. And you can see the front of the cold air spreading like a wave. And absolutely everything radiates in the same way. The higher the temperature, the shorter, but more intense its electromagnetic wave is. And all these waves, as we already know, even in the absence of visible light, create electromagnetic noise, which surprisingly hinders other elusive invisibles.
Interferometer is a device for observing interference, which serves for measuring distances very accurately. For example, interference was used in observing gravitational waves. So it turns out that this is the vacuum noise of light. Yes, that is, which exists when seemingly there are no photons. So it really hinders these measurements. That is, it is just detected in the measurements, so it limits their accuracy.
Or you can say that it reminds this white noise when the TV signal disappears gradually and
Yes, some small details are especially difficult to see on television.
This is the main task of the laboratory of Alexander Lvovsky, to make the electromagnetic wave silent. But how to do this if there is noise even in the absence of light?
It turns out that you can add photons, but at the same time, this noise of the electromagnetic wave will decrease. Such a paradoxical phenomenon, like many in quantum physics. So this is one of them.
So you need to squeeze the light?
Yes, that's right. We use this term compressed light, or compressed vacuum.
Compressed vacuum. Yeah, quantum optics is a very difficult thing, but only at first glance.
Well, in fact, this complex physics that we saw in the laboratory, this red light, blue light, mutual transformations, can be explained in a very simple manner with the help of ordinary children's swings.
So here they are, swings.
Yes?
Blue and red, so...
I do not know how, unfortunately.
But you try too.
Yeah,
If you decided to explain, so... Everybody knows the swing. Now we swing, so...
Look, we were doing this in our childhood. Sasha did it more often than I did. And swinging on the swings. How did we swing? We bent our legs forward, not backward. Sorry, on the contrary. We stretched our legs forward and bent them back.
That's why you did not learn how to swing. Okay.
In fact, this process has a deep physical nature called parametric amplification.
If we imagine the swing as a pendulum system, then every time we change the position of the legs, we change its basic parameter, length. It turns out that length varies twice more often than the natural oscillation frequency of the pendulum itself, twice per period.
Thanks to this, we can actually swing, if we do it right, with the right phase.
I think you've nailed it.
That is, at the right time. Well, not yet, but now we'll see. And if you do this wrong, with a wrong phase, at a wrong moment, then instead of swinging, we will, on the contrary, suppress our fluctuations.
Is it the way you are doing it now? Are you stopping?
Yes, sooner or later, we'll stop. So?
But how does this explain what happens to the light?
And look, the same thing. There is a blue color with twice more frequency, and a red color is half the size. The blue color suppresses. The red vacuum suppresses these vacuum fluctuations, the vacuum noise that we saw, and can extinguish them, practically to zero. Now let's open this stub and let the blue light into my crystal.
That's it, the vacuum has disappeared here and the compression of light began here?
Compression of light began. The blue light began to send a signal to our swing and extinguish their vibrations.
There are more photons, but on the oscilloscope at that moment, whoops, the wave comes to life, and as if it begins to breathe, becoming bigger, then smaller. Hence, when the blue light falls into antiphase to red, the waves are superimposed and extinguish each other. Changing the phases of blue light, scientists are probing the parameters, trying to finally master these electromagnetic swings.
While detecting gravitational waves, we used compressed light with noise suppression more than 10 times. This allows to increase the sensitivity of the interferometer more than 10 times.
Well, that is, by and large, allows us to dive under this level of noise and literally see the world in a way that nature did not create for us?
Yes, we see less noise than when the lights are off. This is absolutely incredible and paradoxical.
It's a paradox, but it's even easier to get rid of the ubiquitous waves of the infrared range for the characters of the movie Predator to know. I heard that there is one very transparent, but insurmountable obstacle for the thermal imager. Is that true?
Yes, it is. This is ordinary glass.
Now we will have a chance to check in. Here's the glass. And now I'm like, I think, the Cheshire Cat from Alice in Wonderland. There's only a smile left after me. Usual silicate glass with a thickness of 1 centimeter absorbs only 1% of the visible spectrum, and at the same time blocks the path to 50% of the infrared spectrum, mainly in the medium and long wave range. And living organisms emit long waves.
For the thermal range, glass is completely opaque.
And here it is, such an unobvious but very simple way to hide from the all-seeing eye of the thermal imager. Oh, and I disappeared. What is it much more difficult to hide from? And how do radio waves affect us? Who sees the world in pink? And how does the camera differ from our eyes? We'll talk about this in the next part of the movie. You cannot hide from what lies beyond the infrared spectrum using ordinary glass. Radio waves are everywhere. The largest natural sources of radio waves are lightning, and of course space objects, stars, galaxies, black holes. But in the 20th century, radio waves descended from heaven to earth. It's strange that Henry Hertz called radio waves useless once he discovered them. The whole modern civilization fell into the network of this range. Telescopes, radars, communications, electricity, internet, radio, and television. All of these are electromagnetic radiation of the radio frequency range. The length of radio waves is large, from 0.004 of an inch to more than 62 miles. Because of this, they almost are not reflected and not absorbed, overcoming huge distances.
As soon as we approach the megapolis, we immediately start getting into this kind of very complex cocktail of fields. That is, it is a very definite and precise term, electromagnetic pollution of the environment. It is still a different kind of matter, which we know very little about, and there was not any during the evolutionary period. And in fact, now, when we place a human in such fields, in such a mix, as we said, we influence his life processes actively, and they are very diverse.
The research in the field of the radiology of electromagnetic fields has been carried out for half a century in the laboratories of the non-ionizing radiation department.
So now we are standing in a screen room. It's an anechoic chamber. It's located on the -2nd floor.
And what's going on here? This is some kind of strange construction, looks like an arena.
Well, almost. Here, the influence of the base station on a living organism is simulated. This is a stand. It's made in the form of a circle, and the antenna is the source.
This antenna simulates the radiation of the telephone exchange, and living organisms are, of course, laboratory rats, and we place them in special cells. Doesn't want to go in there. Since all animals are equidistant from the source of radiation, they will all receive the same dose.
The irradiation with intensity about 500 microwatts per 0.15 square inch is carried out every day during the month.
For two-legged residents of Moscow, the maximum allowable level is only 10 microwatts per 0.15 square inch. That is 50 times less. And such intensity can be found only maybe in a couple of yards from the base station. But nobody still has thoroughly studied the influence of these stations on bio-objects in Russia. And here, by the way, you have something interesting. The papier-mâché of the human head. What is it?
Well, that's a model of the head. This is also for modeling. The subject, it is hollow. The material that models the property of tissues is placed into it. That is, this is a special material, and there are sensors inside. The irradiation is carried out, and we see what dose is received.
But still the rats are more informative, right?
That's right, because this is a whole system, and here we watch the reaction of the whole organism.
Well, it's time for irradiation.
Yes.
Poor creatures, bye. The creatures will stay here for 8 hours. This is exactly the kind of experiment that helps scientists to extract data on chronic irradiation of the body. And nowadays, surprisingly, the amount of this data is rather small, unlike high energy and short-term effects of irradiation. Even this norm for a resident of Moscow, 10 microwatts per 0.15 square inch, was totally out of the discussion. This standard was used only for radio engineering, objects of military design, which are only some units per huge territory. And today, there are almost 2 million base cellular stations in Russia, and a quarter of this amount is in the central district only. Most of them, of course, in Moscow. They irradiate us simultaneously at different frequencies and with different modulations. This is the ocean of radio waves, and we have just begun to learn about their influence on us.
We also got the immune system reaction. That is, the immune system certainly reacted for such kind of constant impact. And they got a teratogenic effect. That is, the serum obtained from the brain of these irradiated rats. We injected it into pregnant females and observed the development of an autoimmune reaction and development of it in offspring. That is, offspring also did not really survive in this situation. It sounds pretty hard. It's almost like some kind of electromagnetic AIDS. But once again, you have to understand that it, well, has nothing to do with real life, nothing at all. That is, a human never meets such conditions, even in this cocktail. He doesn't meet it. The problem in general lies on a different plane now.
Now scientists are most of all interested in the closest and complicated fields. Simply speaking, mobile phones. It seems that these radio frequency transmitters are low power, but in such a close zone, the induction zone, the electric field and the magnetic field impact the brain simultaneously. It creates electromagnetic pulses and induced currents. In short, the whole electromagnetic storm.
Do you have a mobile phone?
Yes, I do.
Very good. Here we have a specially prepared place to set your mobile phone.
Yeah, that is, I put it here. This must be the first rabbit in the world to speak on the cell phone. We're putting the rabbit's ear to the mobile phone.
Yes, for it to fit to the sensor in the nearest area to the cell phone antenna.
The sensitive optic fiber sensor measures the microvesage of the animal's vessels. However you look at it, the rabbit is an ideal tester. The field for experiments is great, and the physiology is very similar to man.
Now I'm going to make a call. In the nearest area, the radio frequency radiation is split into electric and magnetic components. Our hypothesis is that the magnetic field affects the passage of erythrocytes through the rabbit's ear vessels.
The thing is that these main cells responsible for transferring oxygen from lungs to all the organs, erythrocytes, are covered with a membrane containing glycophorin, a protein. This is what makes red blood cells negatively charged. This thing solely helps them to push away from each other and not stick together while passing through the narrow vessels. Under the effect of magnetic fields, cell phones, or say magnetic storms, the electrical potential of red blood cells changes. Thrombi are formed, oxygen exchange is slowed down, metabolism reduces, and then ischemic strokes and heart attacks happen.
However surprising this may be, no one actually tried to check it when the phone is used and placed in the nearest area. No one actually did that. Although a large portion of electromagnetic energy is absorbed by the head tissues. This peculiarity is not that it's powerful or not, but that it is purely electromagnetically designed in such fashion that the energy goes straight into the head.
No, sit still.
The recording is actually going to end now. We've already got 4 minutes.
4 minutes every day with each of the 20 rabbits. The experiment has just started, and these spectral data are to be processed yet. But I hope that they make at least one of the aspects of the influence of electromagnetic field on us clearer. Foreign colleagues from Austria and America have already discovered in their research the correlation between non-intensive chronic radiation and oncology. Swedish scientists have identified inhibition of cognitive, that is, mental functions of rodents. Our local epidemiologists, a decrease in intelligence, and children's predisposition to leukemia. But the data is still very small, even 30 years into the epidemic of mobile communications. What are we even talking about? That's terrible. Even our chute can display how many mysteries the electromagnetic fields still keep.
I can't tell for sure, but I'm guessing that the electromagnetic field that is generated supplies current to the nerve, as it is basically a wire.
Repetition of the Danilevsky century-old experiment in physiology.
Go ahead.
Made all modern physiologists scratch their heads.
Take a look. This is a spasm. Looks like a spasm. Right, a spasm. A strong one.
Before our shoot, it was believed that a brain is required for the spasm, a difficult reaction of the body, but there is no brain as you can see here.
You'll give us a piece of this spasm later, okay?
All right, this one, okay.
If you take a phone half a yard away from your head, you basically secure yourself. Put a wired earphone or a wireless one. There is no actual difference. Then, of course, there is time. There is always time. Reduce talking time. It would be about an hour per day. According to the data from French epidemiologists, they reduced this time to 30 minutes.
We wonder, is it possible to hide from these invisibles? You're going to be surprised, but the scientific city of Fryazino is the place where there are no electromagnetic waves or even magnetic fields on the Earth. Is that right, Alexander?
Alexandra, there are electromagnetic waves here, as well as radio waves, but they are very weak.
Right, but how can we prove it to our viewers?
Well, for example, we can take a device we have, the device that determines field density. Even if we look here, the numbers are going to change. Here are 20 volts per yard, and now 25 volts per yard. Well, this is determined by the equipment working in the room. Computers working, that is.
But there are places where these laws do not apply, right?
Yes, there are specially designed premises in which electromagnetic radiation levels are reduced for. One of the examples is the anechoic shielded chamber located nearby. And here, if we measure the field density, we will see right away that the field density level is about 0.7 to 0.6.
Even lower, that is.
Even much lower than in the next room.
These levels are so small that we can disregard them. Not even in the place most distant from civilization, we could find 2 smaller radio waves.
In addition, we are reducing the level of the magnetic field, constant magnetic field of the Earth.
In fact, this is 282 cubic yards of electromagnetic vacuum, an iron box, the walls of which shield external interference. On the inside, the walls are covered with special additional conical wedges. They are made from polystyrene with the addition of carbon and absorb the inner radiation. Why do you need all this? What is the reverse hedgehog for?
Well, all this equipment is needed to perform electromagnetic compatibility tests in the field of measurement of radio frequency field created by tested samples.
Today's sample is this laptop, but this is used as well to check not only household appliances, but also onboard navigation equipment of ships and aircraft. The problem with modern technologies is that they produce waves of higher and higher frequencies, up to 6 Hertz. The more the frequency of the wave, the less its length, but the higher its penetrating ability. Is this laptop safe? This antenna will be receiving electromagnetic waves from the test sample. That's it. Now, everyone leaves the chamber.
Well, let's get down to measuring radio frequency field.
Let's start. Each device, depending on its purpose and field of application, has its own norms that cannot be exceeded. Sergei enters them into the receiver and activates the antenna, literally by pressing a single button. And we've got a running curve. And by the way, there's actually a peak.
Yes, here. We can even look at it. Interference at a frequency of 542 megahertz. Its level amounted to 53 decibels, and it exceeded the ghost requirement by 6 decibels, almost by 7 if we round it up.
This is a serious deviation, actually.
Yes. Let's say we've got a monitor connected to the laptop. Accordingly, if the interference exceeds the normal level, it can somehow influence the monitor in a bad way. We can see this interference in the form of some ripples or stripes on the screen.
Since you check not only laptops, but also vitally important devices, such as medical equipment, radio navigation instruments here, such interference and influence can, therefore, cost someone a lot, if not their life.
Well, yes.
So a laptop can be dangerous for other electrical devices, but how resistant is it itself to induced radio interference? This antenna is not just a receiver, it can also become an emitter.
Well, in this combination of a generator and an amplifier, we can create a field density of about 30 volts per yard. This is even more than the power of a basic cellular communication station.
You mean those huge towers spreading the signal for dozens of miles around are even weaker, right?
Yes.
Wow. And we have it all right here.
Yes.
A third of these capacities would be enough to test laptops. Oh. You can hear right away that it is the amplifier. Well, and then?
Here, and we're starting the frequency search.
The computer is now assaulted by radio waves within a huge range, from 80 megahertz to 1 gigahertz. And you're waiting for the failure to happen?
Yes.
But here, the tested one stood the test. It's a pity it failed the first stage. It will need further improvement. But now you know that all your gadgets appear to be here before coming to you. Here you are noticing smallest changes of these electromagnetic fields and waves.
Right. Yes, yes.
Seeing the invisible, that is.
Yes, you could say so.
But I wanted to test more than just a laptop.
Another room of ours is a radio-shielded hull, but a bigger one.
But there are also no electromagnetic waves.
Right, there are no electromagnetic fields and radiations at all.
Well, Andre, then I'm offering you to conduct an experiment.
Go ahead.
There's a suggestion that the absence of electromagnetic waves can also be harmful. Sure, we can't leave a man here, but I think we can very well replace him with his ficus. Yes?
Let's leave the flower here.
Yeah, we'll leave the flower here.
Right, and we have to create identical conditions. The light, watering, like with any other flower.
But you're responsible for it now,
All right, I am.
for the next 3 months.
Fully responsible.
Well, good luck.
Yeah, thank you.
And for you, best wishes staying. See you. The second ficus, the control one, I'm also leaving here in Fiazino, but outside the shielded chambers. Except for electromagnetic fields and waves, the conditions are the same, artificial light and watering. We'll see what happens in 3 months. And now, let's go back from the radio range into the infrared spectrum. We haven't seen anything yet in this red light. The Church of the Savior on Blood. Regardless of the name, it is one of the brightest landmarks of St. Petersburg. Thousands of tourists, clicking their shutters without stopping, come here daily to take a photo of this landmark. Yeah, thousands of similar photos will scatter all over the planet. I wonder whether we could take a photo of this place, unlike everyone else does. Oh, Dmitri, hello.
Hello.
That's you I've been looking for. You're a professional photographer.
Right, for example, I don't take simple photos. I take infrared ones. This is the spectrum in which photographers don't normally work, and the photos are completely different.
The mirror camera is very difficult and designed just like a human eye. Both the camera and the eye perceive electromagnetic radiations, focus and turn over the image, and project it. The camera on the matrix, the eye on the receptor cells. But the spectrum of our vision is limited to 3 types of these receptors, the cones. Each of them can intercept its own range of waves. As a result, our vision has 3 main colors, red, green, and blue. All the other waves are simply not received. The camera works in a similar fashion. Before the matrix, there is a bare filter, every cell of which consists of 2 green, 1 red, and 1 blue pixel, RGGB, the same color filtration as in our eyes. But there is also another filter before the bare. It is called hot mirror.
It cuts off the extra spectrum, which gives out the shadows and wrong shades, the ones that are wrong for them, because our brain interprets them in such a way, for example, perceives black as black. But if the infrared spectrum disappears from there, we will see some kind of burgundy, for example, a burgundy jacket instead of a black one. It will be unusual for us.
Hot mirror reflects the infrared light almost entirely, but if we remove this filter from the camera will see everything, including the invisible range. We could do it in an even simpler fashion. Without removing the inner filter, we can install another one on the lens, the one that will cut off not the infrared light, but the visible one. Then the matrix will get tricked and try to catch at least something, for example, the barely visible infrared light, in this focused darkness. Here is the wonderful green glass. Well, but this one is totally dark. I can't see anything through it, even the sun.
This is the best filter that cuts off the visible spectrum completely. This is why you won't be able to see anything through it. If you can see anything, it means that the filter lets the visible spectrum through.
Right, let's put it back in place, and you'll show me this magical picture that no one actually sees.
Sure.
Dmitri only takes photos in sunny weather when the intensity of IR radiation is maximum, and only after a long exposure to collect more of this invisible light. By the way, Robert Wood, physician and photographer, invented this method as early as 1910.
Alexandra, look at the picture.
All right. Well, everything is very, very red. Is it all red completely?
Yeah, this is how it's supposed to be. Well, this is an infrared photo.
Well, frankly speaking, this photo doesn't impress me much. 50 Shades of Pink.
But if we turn it to black and white, everything will play with completely other shades. Some details become lighter, for example. The red brick and the blue details become darker. That is, a higher contrast is achieved with the help of filters. And we get the main thing. We get the details we usually see with one level of brightness with another level of brightness on a black and white photo.
Let's take another look. Here's the original photo in the visible spectrum, and here's the same church in the infrared spectrum. If we turn the visible spectrum into monochrome, we get this. Quite a plain photo, there's not much contrast, and the sky looks pale and colorless. But if we do the same with an infrared photo, we get this. You think there's almost no difference? Wrong. Compare for yourself. Pay attention to the portal. The patterns become much clearer, and the windows become almost black. You remember that the glass absorbs infrared waves. Light and shade here depend not on the visible spectrum, but on the ability of an object to absorb or reflect the IR spectrum. The sky absorbs it and darkens. The clouds, on the other hand, reflect it and become even whiter. The photo literally glows with this invisible infrared light.
Yes, the golden domes are burning. The sky is dark, almost black at times, and the building is light. This is the essence of infrared photography.
As a matter of fact, many insects, such as mosquitoes, bugs, mites, and reptiles, such as lizards and snakes, are sensitive to infrared radiation. They perceive it with the help of special receptors. But this one, burrowing mantis shrimp, seem to be the only one that can actually see it. The eyes of this inconspicuous creature contain not 3 types, like our eyes do, but 16 types of visual receptors. Indeed, this is funny that we, the pinnacle of evolution, are far behind some kind of shrimp. Our ancestors were the ones to blame for our limited capacity. Small rodents sacrificed additional cones, the color receptors, to evolution in exchange for the rods responsible for night vision. Ever since, our picture of the world has been incomplete.
Actually, the green looks most interesting in the infrared spectrum.
What happens to it?
It obtains violet, pink, and other shades of red. When you convert it to black and white,
So,
it becomes very light, almost white. It would look like that in the winter if it was covered with snow.
it means that we appeared in the winter now in the middle of the Petersburg summer?
Yes, in another dimension, in a sense.
Plants reflect infrared waves, protecting themselves from excess overheating. And the water?
The water in the visible spectrum is usually grayish,
Yes, a bit green, we can see it from there.
but in the infrared spectrum, it is totally black, as it absorbs the infrared spectrum. The photo becomes very contrast. White leaves, black water, gray buildings. That's what you need for a good photo.
I'm not sure I would be glad to always see the world from this side of it, but I'm very glad that with the help of the camera and filter, you can open your eyes to infrared electromagnetic waves. Open your eyes in the direct sense. The plastic of your shades is absolutely transparent for these waves.
I feel how varied the world is, how global it is, how small we are in it, how little we know, and how much we have to study it yet.
Now's the time to check how the ficus in Friazino is doing. It has spent 3 months in the chamber shielded from electromagnetic waves. Judging by these pictures, it has been watered regularly, but we'll check the second plant first. Here's our reference.
Here, this is the reference plant.
Listen well, everything's fine.
Everything's fine, like a new one.
Even without natural solar light, this ficus did well, without light, but with electromagnetic fields. What about our main tested one? Andre, tell me the truth. Have you watched the result already?
I did. I visited it once a month to watch it.
We couldn't predict the results of this experiment, as I didn't manage to find any data on similar research.
Look what happened to this one.
And here, well, there's not a damn thing left of our ficus.
Yes.
Everything's bad, generally. Look, its leaves have almost entirely fallen off.
Everything's bad.
Horrible. And this, considering the fact that the ficus is one of the most enduring and unpretentious plants ever. Regardless of the electromagnetic contamination of the modern world and the harm inflicted by it, there is also no life without this invisible force, a paradox. did this experiment surprise you too?
Frankly speaking, we weren't expecting such a result. Right, you could say it surprised us, yeah.
What surprising things these invisibles are, the electromagnetic waves. And here's how their absence influences us. Yeah. The film turned out to be very complex simply because explaining what invisible electromagnetic waves are appeared to be as difficult as trying to see them, or as trying to teach a physician to rock on swings. Difficult, yet possible. We traveled beyond human abilities and saw another type of matter. Not a substance, but a field. Not researching something beyond our vision is the same as playing within a single octave. Well, can it even compare to the full picture? By the way, have you noticed that we still haven't gotten to the ultraviolet? Right, that's the next part of the film. What do the invisibles hide? Ahead to the ultraviolet. And for now, the concert is over.